Hello, everybody. Welcome back to the afternoon of talks that we have for today. And so we're going to be starting out with a pretty interesting workshop here. And so we have a few different speakers actually for this one. And so first off, we have Shirley Zan, who is the first year rep for the Carleton Computer Science Society. And so she'll be talking to us about creative coding and then walking us through a workshop to create some pretty awesome stuff. Then we also have Dr. Dave Mold, who is a professor at Carleton University. He teaches various grad courses and game development courses, and so you might recognize him from some of your classes already. And he's the lead of the Graphics, Images, and Games Lab at Carleton. And so throughout this presentation, for either Shirley or Dr. Mold, if you have any questions, feel free to put them in chat, and I will make sure to pass them along to the respective speakers. This workshop will work a little bit differently than the rest, where we will be, instead of just having a lecture, you'll be able to follow along with some of the code throughout the talk. And so in the Discord channel that accompanies a live stream, I've posted a link that will have different references that are discussed through the talk, but also the code that you can start out with and you can examine and just get started with. I do also want to mention there is definitely a lot of more advanced concepts in this talk, and so if there's anything that's as complex as I mentioned, feel free to ask it, and we can get that answer for you. So without further ado, I'm going to pass it over to Shirley, who's going to get started with this workshop.
Thank you, Forrest. Hello, everyone. I'm Shirley, and as Forrest said, I'm a first-year rep at the CCSS, and today I'm here to do a workshop to introduce everyone to creative coding. Let's start and look at a little bit of what's going to happen on this workshop so we know what's going to happen down the line. So first, I'll do a small introduction to creative coding through my presentation, and then Dr. Mold is also going to do a little presentation onto the more theoretical side of creative coding. And then after that, I'll be doing a little code demo in p5.js by creating a flow field. If you don't know what it is, just look at that image on the third and kind of see what it is. I think it's a pretty beautiful kind of artwork to recreate. Let's start by having the definition of creative coding. Creative coding is a type of programming where the goal is to create something expressive. What does expressive mean? Well, art is expression. I'm sure you've all seen some art in your lives. Paintings, sculptures, games, film, literature, even music. Creative coding is the act of creating art like these, but through code. Yes, all of the art that I mentioned here can be somehow created through creative coding. Creative coding is a huge field that has many different applications. One example is digital art. Now, when you think about digital art, you probably think about digital art pieces created through softwares like Photoshop or Procreate that kind of imitate real-life art tools. Well, this is an example of digital art. When we talk about it in terms of creative coding, we tend to see a lot more art pieces that are created with algorithms or processes in mind. After all, the biggest advantage of coding is that it is in its ability to do really huge calculations. Here we have some examples of art done with creative coding. As you can tell, many creative coding art pieces have these kind of impressive patterns and color changes that you can't really do manually or on your own hand because it's just too much calculations, right? In fact, there's even a form of creative coding called generative art, which solely rely on using processes to create art. Generative art, by definition, is a form of creative coding where art is created through a process, which in this case can be a set of rules or it can be a computer program, etc. A process in this case, oh, sorry, my bad. Here, I just want to illustrate some examples of generative art. Yes, another collage of art pieces. Even if you feel like these generative art pieces are a little bit too complicated, you might not kind of get it. If you think about the tiled floors on different buildings, or you think about brick walls and those repeating kind of rectangles or like even squares, those are a very simple form of generative art. Now, after some digital art, we're going to move on to physical installations. These are interactive art installations, which are physical exhibits that help bring art into real life. They're often done in museums or they're done during brand advertisement campaigns. For example, the picture on the left and the right are examples of companies like Meow Wolf or Arctic House, which are both ones that specifically create interactive art installations. As for brand campaigns, more and more companies are getting into this form of art due to its new kind of popularity. So Nike, for example, uses this fuel band wall as a way to promote their product. And you can tell by the middle, by this man touching the wall, it changes the color whenever he touches it from the red to the green. So that's a form of the interactive art installation. Creative coding is also used in data visualization. If you see any kind of data analysis video, which you probably have since our past 2 years were very busy due to COVID, you've probably seen some data visualization. Sometimes, other than using the usual graphs and charts, it can also take data to convey messages in forms of art. For example, the piece on the very right, Fossil Fuels, created by George Ray, uses data on climate change to create a piece which tries to display the effects of our carbon emission. Okay, so I think we all have a good idea of what creative coding kind of is and what some of its applications are. So right now we're going to take a look into some of the softwares used in creative coding. So the first is Cinder, which is an open source library designed with C++. It's useful for abstract projects like art installations or commercial campaigns. There's also Processing, which is a graphical library and IDE designed with Java. It has a graphical interface and simpler design to help non-programmers. And it also has many different kind of counterparts. So there's a JavaScript version, which is p5.js, what we're going to be using later. There's also a Python version. So if you want to play with that. The third software is Open Framework, which is an open source toolkit designed with C++. It has a large dependency on open source libraries because C++ on its own doesn't really have that many media related stuff. So the good thing about this is that experienced programmers will have a lot more control and transparency with this toolkit. Okay, so I know I talked a bit, but right now I'll be somewhat done with my introduction presentation. And right now I'll be handing the stage over to Dr. Mold as he'll do his own presentation on some of the more theoretical stuff in creative coding.
Yeah, I don't know whether I'd characterize this presentation as theoretical exactly, but yeah, just to give you some additional examples of some things, projects done a little bit closer to home than the ones that Shirley showed you. I don't seem to have the ability to move the slides. Okay, there we are. Right, so Shirley described creative coding as using code to create aesthetic objects rather than something more functional. And this is certainly the direction that I'm going to be talking about here. I work in the area of computer graphics, which in computer science is a little bit of an unusual area in being situated somewhere between science and art on the other hand, and having objectives that aren't purely functional, but having some sub-objectives of creating tools for creating images and creating the images directly, whether through simulation or using some other approaches, using genetic algorithms or deep learning or what have you. And as Forrest mentioned, so I help to run the Giggle Lab, and this is one of the graduate labs at Carleton. The URL there, if you want to have a look at some of the public-facing stuff. We've got a group of graduate students that are working on various projects in the general area of computer graphics. And one of these areas that we've put a decent amount of effort towards is image stylization, the sub-area of computer graphics where you take in an image, generally a photographic image, and you apply some kind of transformation to it to make it look as if it had been created through some traditional artistic process or using some traditional artistic media like stained glass. And we've got a number of such projects that we've done over the years. The general ethos is that it's a way of creating aesthetic images or aesthetic objects, but instead of using the craft and tools of a traditional artist, our tool is code, and we employ algorithms and mathematics in the service of creating the images and aesthetic objects that we're manufacturing. And to provide a simple example, here's a photo that's been automatically modified where the center of the image has not been changed very much. And so if you look at this without paying a lot of attention, you may not at first recognize that it's been altered. But as you get further from the center out towards the outside, then there's a progression where it becomes more like watercolor effect or some kind of painted effect. It becomes more abstracted. The forms are still present, but they're not as forceful and not as clear as they are towards the center. And so this is what I consider to be an interesting effect. And as I say, it's generated using algorithms and mathematics, and of course, underlying all that, the code. And you might think that in order to get to a process like this, you need to spend a lot of time sitting and thinking about what to do and planning ahead. And before writing any code, you do some integrals and you draw up a software engineering plan. And certainly that is a strategy that we've employed. There was a project that Forrest actually spent some time working on as one of a few team members, where we were trying to create pebble mosaics out of images. So have an image and communicate the image through a collection of small primitives that resemble river eroded pebbles, these rounded shapes that when assembled into the configuration shown, communicate the content of the image. So there's kind of this double layer of the individual pebbles and then the aggregate showing the content of the image. And for this project, we knew what our goal was, and we had some algorithmic tools that we knew about that we were going to deploy in service of this final look. And we put it together over the course of a good long period of time, and eventually got something satisfactory. And there's some nice effects in here, some subtle effects where, because the pebbles are three-dimensional objects, we're able to do some conventional rendering, and you can see the progression of the lighting. You can see at least a little bit the three-dimensional shapes of the pebbles, and by having the pebbles connected to the underlying image content and having them inherit some color from the content of the image, then they communicate the overall effect of the input photograph, and you can tell what it is. I hope you can tell what it is. And so that's one approach, just having a goal in mind and assembling the needed tools to be able to reach that goal. And that's certainly not the only way to work. And in fact, maybe I should say it's not my preferred way to work. I prefer a little bit more chaos and a little bit more of a process of discovery, where maybe you don't know where you're going to end up, but you hope to find something interesting along the way. And this is the outcome of a project where we didn't necessarily know what we were going to find at the end, but we had some ideas of taking an image and dividing it up into highly irregular components that nonetheless the regions that we ended up with had some relationship with the underlying image content. So there's a region boundary at the location of object boundaries in the image. So the sunglasses have some boundary. The neck of the guitar has a well-defined boundary, and then we colored these regions in different ways to give some appearance of chaos, and not coloring them in remotely a realistic way, but having an attractive palette of colors used to communicate the image content. And even though you wouldn't imagine finding an image, you go to your house and you won't expect to see anything like this, but you can still tell what it is, and you can imagine seeing a scene like this, even if colored not in this radical way. And underlying all the methods of in creative coding, not necessarily to this level of sophistication of mathematics, but there is going to be some mathematics underlying it, and that doesn't mean that you have to plan everything out and you have to know how the math is going to come out. Sometimes you build something and it looks great and you have no idea why. And for the purposes of art, that's totally fine. You can stop there. For the purposes of science, that's not very satisfactory. And you will want to find out why it works and under what conditions it works, and to describe it to other people in a way that they can grasp it. And the way to communicate algorithms that have a significant degree of complexity. Okay, you've got the code, but also you can abstract away the code. It may not depend very much. The image may not depend very much on specific details of the implementation. You can have equivalent implementations that produce the same output. But underlying it, there is this mathematics, and having a mathematical description of what's going on is something useful for the scientific pursuit. And if by chance you find yourself so interested in this area that you decide to do graduate work in it, that you want to pursue it in a scientific way, then the art side will serve you well as you get some results that look interesting, that look beautiful, but then you also provide a description of that is timeless and precise, and the language of mathematics is the way to achieve that. And even if you are lucky and you make a discovery, then there's still long nights or early mornings, or maybe both if you stayed up all night, a good amount of work in putting it together into this precise way and finding out what the possible behaviors are of the method that you've created, and what the limitations are, and distilling it down into this precise description. But that's really not the fun part. The fun part is doing the exploration and discovering these things along the way. And I thought I would springboard off of this example and take a moment or two to give some flavor of what might be involved in coming up with this. So this, in this approach, I've simplified it a little bit. So this is a little bit deceptive in its presentation here. If you want to get all the details, go and read the paper that's been written about this. But just to simplify things, to give you a sense of what's going on, what we've got here, there are a number of nodes scattered over the image plane, and we do least cost paths through the image to find out to find our subdivision, to find out which pixels are closest to which site. And you get a region by taking the set of pixels closer to this site than to any other site. And one of the elements making this interesting is modifying the shortest path calculation. If you've got a path, the distance along that path, so starting at 0 at the center, and as you go along, if you've ever looked at shortest path calculations, or even if you haven't, this is the obvious thing that you do. You've got a sequence of edges, sequence of weighted edges, and you add together the weights of all the edges along the way. This is the natural thing to do. This is what is nearly universally done in shortest path calculations. Is it the only possible thing you could do? Obviously not. Maybe you, in me saying that, you've got your own ideas of how this equation could be modified. I will postulate a moderately simple alteration to this equation that has fairly profound effects on the resulting regions. And this modification looks like this. So instead of just taking the sum of all the edges along the way, we're still going to do that, but it's only one term. We've got the second term, arguably the dominant term, where we take out of all these edges along the path, we take the biggest one. So the set of edges, Wi, we find which edge is the most expensive. And we multiply that edge by some factor gamma, maybe a very large factor like 1,000. And if we use a very large factor, what we're doing is telling the shortest path method to take the long way around. Don't take any shortcuts like climb over a wall, go all the way around the wall. This one expensive edge is now intolerably expensive, and it's much better to take a large number of cheaper edges. And this causes the resulting regions to become more irregular, to get them to correspond better to edges in the underlying image, and you can get an outcome that looks like this. And of course, color it in a different way. So this is a different palette being applied over the same set of regions. So this maybe gives you a little bit of insight into one particular example of what this might look like. One of the staples of creative coding, one of the very common building blocks, is particle tracing, where you've got some dynamics for your particles, whether moving around in some kind of flow field or vector field, or following a simulation, or having some dynamic behaviors like flocking. And here are some outcomes of particle tracing. So the idea here is that you're moving the particles in some way, and each particle is leaving a trail behind it as it moves. And on the left, we've got a traditional simulation-based approach where there's no particular organization of the particles, just they're moving through a common set of forces. And on the right-hand side, the particles are interacting with one another and communicating with one another, and it gives the illusion of some kind of surface, perhaps, where the apparent surface is fluctuating and wavering, and we've got these cues like the lines moving closer together or becoming further apart, or cues of occlusion where the particles seem to pass below the surface, or the lines seem to pass below the surface. A very strong cue in human perception for giving us the impression of, giving us the ability to interpret what we see in front of us in the world, and here kind of hijacked to provide an illusion of a three-dimensional surface, even though the particles are moving strictly in 2 dimensions. Once you've got the idea of the particle tracing and the idea of having the particles stop when they run into a previous trajectory, you can use this to subdivide the image plane into regions, and then you can color these regions in different ways, perhaps in some arbitrary way, perhaps through some other algorithm, perhaps through taking on the colors of an underlying photographic image. And if you've chosen your image wisely, and it's got a good set of colors, then you can get an interesting looking output from that. There's a lot to be said for leveraging the aesthetics of photographic image as a source of data for for your creative coding undertakings. And for that matter, why stop with one image? You can get tons of images, and in a big data or machine learning type of approach, you can have the computer grind away and extract some interesting structures from the image and come up with some output on that basis. There's often a lot of hard work underlying the creative coding. Part of the value of being a programmer is that we're able to offload a lot of that work to the computer, and you can write a relatively short program that can get the computer to run for a long time and hopefully generate something interesting. There's often hard work on the programmer side as well, but part of the beauty of creative coding is that you may not have to do this tremendous amount of work yourself. No one calculates fractals by hand, but you can make interesting patterns by getting the computer to calculate some fractals. And if you're just delving into creative coding, you don't have a lot of experience yet, then maybe you have to get lucky in order to find something interesting. In the space of possible programs, not very many of them create something beautiful. So you have to use your judgment, you have to iterate, you have to experiment, and maybe you have to get lucky. But if you do get lucky, if you have this cauldron where you've put in various algorithms and changed parameters and assembled some structure, and then you can look at it. There's great joy to be had in the discovery, in finding something, working for a while, and finding something that is an aesthetic object according to your own personal aesthetic, and you can show it to your friends, and to the extent that they share your appreciation of what is and isn't beautiful, then they can also enjoy what you've created. And I want to leave you with the comment that I put up a bunch of reasonably polished images, and I put up some mathematics that may seem a bit daunting, but don't feel like this is an area that's difficult to get into. And I guess part of the next portion of the workshop is going to be about seeing how to get going. And I encourage you to try things out. Just jump in, splash around a little bit, iterate. You're going to have to, your first efforts are maybe not going to produce anything worthwhile, but don't be discouraged. Just try something else. And when you find something promising, then you can follow up on it and refine it until you got something that you're happy with. Or you can just have fun. You might not have a goal in mind, but you're just like a kid in the swimming pool having fun, slapping the water and seeing where it goes. And there's a joy in that, and I encourage you to try it out. I hope I've left enough time for a question or two. And if anyone does have any questions, then I'll be happy to continue the conversation.
Yeah, so we have a few from chat that I'll go over here. So one was asked a little bit early on, so I'm just going to restructure that question a little bit. We explored how we can create some art through like boundary detection and like closest path and stuff like that. But what are some other domains in mathematics that we can see changed over into different fields in image processing? Or like what are some examples of what we might see?
Anything where you've got an algorithm that has a spatial effect is easy to port over to the image domain. So anything in computational geometry or simulation, fluid simulation is a source of inspiration for people doing creative coding. Other kinds of simulation, so physical simulation with discrete objects. I mentioned the particle tracing, so this can this is in the simulation domain. And I didn't talk about this very much, but maybe I didn't talk about it at all. But there's something else in interaction where you provide some cause and effect relationships, and you get the human user to make some manipulations and then see what happens.
Mm-hmm. Yeah, I think that's definitely sort of a good way to look at it with like anything that can transfer to a spatial algorithm. Another question. So this is a little bit more based on the Giggle Lab, and you did talk a little bit about what type of stuff is like researched in there. But can you give some examples of what the grad program looks like for students participating in this lab?
So I'm not sure how to take the question. Are you asking about, for example, projects, or what graduate studies looks like? In some ways, graduate studies in the lab doesn't look very different from graduate studies elsewhere. It's just that the nature of the projects that we undertake. So the structure of grad school is it's a master's 2 years, you do 8 months of coursework and 16 months on thesis. And in the case of a creative coding style thesis, you spend that time developing uh, developing a method to produce something that hasn't been done before. And this is very vague, in part because all these projects differ. But there's typically in the students that I have working on this, there's an initial exploratory phase where we do this splashing around and try some crazy things, and then either we discover something in a short time, something that we think is worth following up on, or we say, look, we're not getting anywhere here. Let's switch to a different style of project, where instead of just trying things, we didn't get lucky, or we didn't have this insight that we needed. So we moved to a more structured development, where we get some inspirational images and we say, okay, we want to create things that look like this, whether they're artistic images or objects in the natural world like trees, or what have you. But then we have more of a well-defined target, and then we think about what kinds of methods we can use to achieve this more well-defined objective.
Yeah, I think that was like a really good way to answer it. So sorry about the vagueness of the question. One last one here. What do you think of math-based art like MC Escher work? Is there any work done in graphics that takes inspiration from something like that?
Absolutely. There's an entire journal, the Journal of Mathematics and the Arts, that does this. And speaking of Escher, Craig Kaplan had a fairly influential is quite the right word, but let me just say interesting, fairly interesting paper in automatically creating Escher tiles that appeared in SIGGRAPH in I don't remember the exact year, roughly 20 years ago. And so certainly historical mathematicians that have created uh, aesthetic objects. I mentioned fractals. So this is something in the domain of creative coding. Uh, you, if you're more interested in mathematics than in code, then certainly there's something there to be explored. I guess I would still encourage you to consider using code to do the exploration, just because doing the graphing and doing all the calculations, as Shirley alluded to, it's much easier for the computer to do it than for the human brain to do it. Knowing more mathematics will help you to pick good equations and systems to investigate, but yeah, having the computer to assist you is invaluable.
Awesome. And I just want to leave this section off with a little bit of a story. I remember when I came to you in my first year and I knew we were going to work on this project together. And I came into our first meeting having scribbled some ideas onto a piece of paper of what I assumed the project to be. And so, just as a reminder, we took a look at some of the earlier slides about like the pebble mosaic. So, an image made out of stones. And I remember coming in and having like some doodles of like how to put puzzle pieces together onto an image and then kind of talk to you about like, I don't understand how we'd be able to generate this because I'm coming at it from a perspective of I'm trying to solve the problem with like the physical world knowledge I have, whereas you very quickly directed me into the sort of area of, well, what kind of mathematics could we use to represent this? And so definitely like bridging that gap between sort of the intuition you might come in with just from the physical world versus what research looks like. So and hopefully we can see some of that in Shirley's workshop. But one more thing.
But if I can interrupt, I
Yes.
also don't want to discount the intuition that you get from the physical world. We live in the physical world, and we have a highly developed intuition about how things behave there. And many of our simulations, things like fluid simulation or rigid body simulation, intended to imitate what happens in the real world. These are well developed, and they're excellent building blocks for doing things in creative coding.
Absolutely, yeah. So there's definitely a distinction between the two. Yeah. So I just remember that as being quite an interesting intro into creative coding for myself. So anyways, thank you so much, Dr. Mold. This was a great presentation.
Thanks for inviting me.
Yeah, absolutely. And so we'll hand it over to Shirley for the workshop.
Okay. Thank you, Dr. Mode. So right now, I'm just going to be talking about some of the ways to kind of get started in creative coding. So obviously, you can stay for the code demo where I'll just be showing a flow field. And through going through the code demo, you'll kind of get some basic concepts in p5.js, and then we'll be able to move on to create some of your own more other projects. There's also the option of just playing with some of these softwares, and making animals or making simple landscapes and just getting started like that. There's lots of tutorials online for free that you can use to get started. So there's lots of ways to get started, and creative coding is definitely, I'd say, not as hard kind of path, not as hard kind of ability to learn, just because I wouldn't say it's as complicated as learning something like data structures or anyways, let's actually get started with the code demo. So let's move the screen share back onto my.
Perfect.
Okay.
And I will just quickly mention for anybody in Discord, I'm posting the links there that you can use to get started. So as Shirley is talking about different links, I'll make sure to be posting them there.
All right. Okay. Thank you, Forrest. All right. So now that you're here, hopefully you're here on this website for the p5.js web editor. Once you're here, the first very important step I recommend doing is to just change your theme to a dark one. I think your eyes will thank me later. Anyways, so once we're here, you should be able to see two functions already set. One is the setup and one is the draw function, and they do exactly what their name says. The setup function is a function that will run once when you start the program, and it will just do some basic setup things like creating the size of the canvas, setting the background, creating any kind of arrays or numbers that you might need for the rest of the program. And then the draw function is the one that will continuously kind of loop through the running of the program, and it'll be used for more specific things like creating the different pieces of artwork or not. So if we run this, you'll see that right now on the screen, there appears this white square. Oh, well, not really white, so more like gray. And this is created because we had this function here, create canvas, which just created this canvas of size 400 by 400. And here, the background is this color because we called this function here background and wrote a hex number here, which is just how bright it is. So right now it's this slightly bright color because the value is quite high. And before we actually kind of get into all the code, I just want to show the finished product so you guys get an idea of what you're creating here. So this is the finished product. I'll just run this. Ooh, quite impressive. I know I showed the image earlier in the slides, but I think seeing it in action, actually being created, probably gives it more of that like impressive ooh aspect. Okay, so let's stop. Let's go back to the empty sketch. What we're going to do right now is first I'm going to be adding a new function, and it's just going to be called mouse clicked. And what this function will do is it will execute code within it once you click on the canvas. And I'm going to add another piece of line of code here, and it's called save canvas. And just like its name says, by including this function running code here, what it will do is once you click on the canvas and you see a piece of artwork that you really like, it will save it as a file on your computer. So this is pretty good if you want to like save all these processes or different kind of art pieces that you think are pretty good. So this will take 2 parameters. The first is the name of the file. So I'm just going to call it art piece. And then the second parameter is just the extension of your file. In this case, I'll just make it PNG. Okay, so now that we got the kind of basic stuff down, right now I'm going to be moving on to the actual construction part. So what I'm first going to do is I'm going to move background, and I'm going to move it into the setup function because this is something that will only run once. And I'm going to change this value from 220 to 0. And this is because I want the background to be a black color so the colors would pop out more. But if you don't want the background to be black, you can of course leave it as 220 or leave it as 255 if you want a white background. It's up to you. And next, I'm going to be also changing the size of the canvas. This is a pretty good looking canvas, but what I want is I want this canvas to be bigger. And of course, you could just write a bigger value, like you could write it as 500 or 600 or something. But what I want to do is I want to make this canvas take up this entire kind of space here. And there is a way to do that by making it so that instead of writing a number for the width, you instead write window width. Width, not weight. Yes, window width. This will just take the size of this entire kind of space here. So once I run it again, the canvas will now become this whole area. Pretty cool. Okay, not the cool part yet. But okay, in order to start creating our lines, we're going to start by creating an empty array at the very top. So we're just going to be calling it particles, and then we're going to be listing as an empty array because we're going to be adding values to it in the setup function. So once we have the empty array set up there, we're going to go into our setup function, and we're going to just be writing out some variables. And I won't explain them just now because I'll be explaining them as we look at the image it produces. And then I think it'll be easier to explain that way. So the first variable we'll be creating is going to be called density. And we're just going to set it to a value of 50. Next, the next variable we're going to create is going to be called increment. And this will just be equal to width divided by density. And you may be wondering, what is width? Well, width is just the width of the canvas. So in this case, right now, I set it as window width. So width is equal to the width of this display area. But if I've set it to something like 400, then in this case, width will be equal to 400. So after that, we're going to be initializing a for loop. So let's have our for loop. Var x is equal to 0. X must be less than width. X plus equals increment. So we have our first for loop, and then now we're going to be initializing our second for loop. This time, we're going to set the var to y equals 0. Y has to be less than height, and then y plus equal increment. If you're a little bit confused right now, don't worry. I'll be explaining this really quickly. So after we initialize our for loop, we're now going to be creating all the different particles, which are going to be creating those lines in the program. And in order to do so, we need to create vectors. And to create vectors, all you need to do is simply write the function create vector. And create vector will take, it can take 3 parameters, but in this case, since we only need the x and y, we're only going to be putting 2 parameters, which in this case is just the x and y. And then after that, we're going to be adding it to the array. And then after we do that, we now have initialized and set up our array, which contains all the different kind of particles in the picture. But right now, nothing is happening because I didn't do anything to the canvas yet. So we run this, nothing happens, of course. So in order to have something appear on the screen, we're going to go into our draw function, and we're going to first write a no stroke function. And what this does is just make it so that anything you draw onto this canvas won't have any kind of outlines. And then after that, we're going to have a fill function. And the fill function does something similar to the background, but what the fill function does is it changes the color of whatever comes after. So the background function basically paints a big, like, one-colored kind of shape onto the canvas, and the fill function would just do the same thing, but instead of it doing it to the background, it'll do it to whatever you draw after this piece line of code. So I'm just going to fill it with 255 for white, and then after that I'll be writing another for loop, this time just setting it as I for increment, and then 0 I less than particles dot length, and then I plus plus. This will just iterate through the array. And then now we're going to be actually drawing something onto the canvas. In this case, I'm going to be drawing an ellipse. And this will just take 3 different values. The first 2 are the x and the y of the center. The third is the radius of the ellipse. So what we're going to have is we're just going to have particles I. So taking the ith value of this array of vectors, and we're going to be taking, oh, my bad, the x particles I dot y, and we're just going to make it so that the ellipse is only size 1. So let's run this and see what happens. Ooh, we have something on screen, a bunch of dots. Now, it may not seem too clear how this is created. And right now, what's actually happening is that I've divided the screen, at least widthwise, into 50 different regions. And all these different dots are just appearing as like on the lines where the screen is divided. 50 may not seem like a good value to see what's happening. So let me just change density to 5. I think it's more apparent now that the screen, at least widthwise, is divided into 5 different quadrants, and the dots are just appearing on these lines that divide the screen. Change it back to 50. And right now, it looks pretty good. We've managed to get all these points to appear on the screen. But right now, what we're going to do next is we have to make it so that these lines turn into, these dots turn into the lines here, which actually move and create the artwork. So in order to do that, we need to set up several variables in the draw function and in the for loop. So the first variable we're going to set is going to be called angle. And what this will do is it will produce angles at which these dots will, at least new dots will be moved in. So it will gradually create these lines. And since the angles itself, we don't want to kind of set a one kind of value of what the angles can be, because as you can tell from the picture itself, all the different ways the lines move in are pretty random. So what we're going to do instead is we're going to be using the noise function. And the noise function just kind of returns the Perlin noise values of the inputs. And if you don't know what Perlin noise is, don't worry. To quickly kind of go over it, because I don't want to go into in depth, here's kind of a Perlin noise function and the random noise function. I'm sure you probably know what random is. Random just produces values, outputs values that are completely random. So as you can tell from the bottom kind of graph-ish, this kind of spiky graph here has all these different values because it produces random values that are kind of unrelated to each other. They don't really look really related. Perlin noise also produces randomish values, but instead of looking at random, what Perlin noise tries to do is to make it so that the values outputted are more smooth and in air quotes more natural looking. And it was created by a man named Ken Perlin for a movie, so that when they were rendering the vase and different kind of objects in the movie, it didn't have to look really weird. So that's the point of this function. So what we're going to do is we're going to write out noise, and this is just going to take particles I dot x. It's also going to take particles I dot y, and it will just take these two inputs and it will output a value from 0 to 1. But of course, we can't have angles that's interval between 0 to 1. It wouldn't have a lot of variation that way. So right now, what we're going to do is we're going to map this function from 0 to 1 to 0 to 360. In order to do that, we have the map function. And what this will do is it will just change your original value from one interval to the other. So let's say right now it's from 0 to 1, 0 to 360. From 0 to 1, let's say it's 0.5. And if we need to map it from 0 to 360, it'll just multiply it by 360 and you'll get 180. So that's just a simple function to help you avoid calculations of like dividing the second interval by a original number and then having to multiply it by decimal. This will just automatically do it for you. Now that we have an angle already created, what we're going to do is break up the angle into its x and y components because we cannot add an angle with vectors because they're not quite the same. So in order to do that, we're going to add the angle itself into the array, but we're not going to add it on its own. What we're going to do is we're going to write the cos of the angle. Oh, my bad. Cos of the angle, and we're also going to break it up into the sine of the angle. Remember a little bit of trigonometry back in high school. This is just taking, finding the x and the y component of that angle, which forms a kind of right-sided triangle. So now that we have added it, let's run this and see what happens. And as you can see, we have something happening on screen. We have the lines moving all over the place, and it looks quite good, but there's a problem. This isn't what we saw on the final output. This looks very fuzzy. It's not really smooth. You said the noise function was supposed to produce smooth values. It's not really smooth here. And the reason why this is happening is because when we put the input into the noise function, these values on their own are actually quite big. As you can tell from this array here, when we added by increment, the values could get pretty high, up to values like 500, 400, even 1,000 or something. And that's pretty big. And thus, that's why the values produced by the noise function look so fuzzy. It's because we're so zoomed out on this picture. We don't see the smooth lines. We only see the kind of ragged, rough lines. So in order to not do this, we're going to have another variable on top. And it's just going to be called ver noise scale. And what this will do is we're going to have this value kind of change your input values onto a smaller value so that when your output actually looks smoother. So we're going to initially set it to 0.005. Feel free to change this to another value like 0.001 or 0.002. It's up to you. And it will have a slightly different effect if you change it to different values. But for now, I'm just going to keep it at 0.005. And I'm going to go into the noise function. And I'm just going to multiply each of these values by the noise scale. What this will do is just reduce these values to a much smaller value so that the output won't look so fuzzy. Now let's run this again. And woo, it looks a lot better now. I mean, still not close to what we have finally, but definitely pretty good. It has these kind of spirally effects. And I think it's pretty good, but we still have a couple of steps to do before it gets to the final product that we saw before. And in order to do that, we're going to go into our setup function here, and we're going to do some basic changes. So the first thing we're going to do is go into degree mode. We're going to write down degree mode. And what we're going to put in here is we're going to put degrees. Now, if you've done, of course, you guys have done math. If you've done math and you work with trigonometry, you know that your teachers will tell you to change your calculator mode to radians or to change it to degrees in order to do certain questions. And the reason why this graph the piece looks a little bit, let's say, spirally is because right now the degree mode is in radians, and that's the default. But we're going to be changing it to degrees since we're working with degrees and not radians. Let's see the change happen. Oh, That's awkward. What happened? Oh, wait, my bad. This is awkward. Ignore that. It should be angle mode, not degree mode. Let's run this again. Ah, very pretty, huh? It's now gradually evolving into what we saw initially. And the cool thing about this is due to the nature of the noise function, if I run it continuously, it actually produces slightly different kind of artworks. And right now, since we're here and we created a basic kind of pretty solid looking piece of artwork, I will now kind of get into messing around with the numbers just right now to kind of see how messing all the numbers really can change your artwork. So Dr. Mode has talked before about how in creative coding, you sometimes don't really know how messing with some numbers will produce what kind of results, because as I said, as he said, the computer is doing a lot of calculations right now that you don't quite know how is resulting into this artwork. I mean, there's this kind of joke in at least beginner programmers is like, oh, well, there's a mistake in the program. How? And then you fix it and you still don't know how you fixed it because of the complexity of some of the programming. And of course, that might not be ideal in functional programming, but in creative programming, it's encouraged to really play with the numbers to see what different kind of artworks might create. So let's go into noise scale. And I've said before, you can change this value if you want. So right now I'm going to be changing it to a smaller number. And as you can tell, whoa, this artwork really changed a bit into something else due to me kind of making the noise scale even smaller. So let's change it back to 0.05. We can even change density to be a bigger number, like 80. When we run it, ooh, now the lines are even smaller and looks quite cool, isn't it? I suggest really playing with the different numbers. Most of the numbers here can be played with to get different effects on the final kind of canvas. So I recommend definitely playing with the numbers. So after this, let's add in a new function. This function will be called noise detail. And what this will do is it will change the way the noise generated on your noise function. So what we're going to do is we're going to set it first to 1, and I'll let you check it out. I'll just change this back to 50 so you can kind of see the different lines instead of being too packed. So let's run this. With noise detail 1, you can see the lines here look kind of like this. They look pretty smooth, pretty rounded and whatnot. And I'll just tell you what happens if we were to change this noise detail to a higher value. Let's see what happens. Let's say it's changed to 10. Ooh, there's a little bit difference in how it's produced. As you can tell, according to my friends who also saw this demo, the lines are a lot squigglier. Yes, they are a lot squigglier. And the reason for this is because we increased the noise detail. By having it be a higher value, this just means that the noise created will be a lot bumpier. It's kind of like having a graph with data that's a lot more that has a lot small increments, hence you see a lot of the smaller changes versus having a set of data that's super kind of sparse between and thus looks a lot smoother. So this is 10 and this is 1. Very different. Okay, so maybe having the grid look like this is a bit boring. And here I'll introduce another way to make it so that the grid looks more interesting. So what we can do is we can go back to our initial setup for loop and we can change it so that the X and Y, originally they're kind of set up in this grid-like way, but what we can do is we can actually make it so that they're added in a more random way. So what we can do is we can go to here and we can add random -5 to, actually let's make it here. Value. So what this will do is we'll take the X that you have here and it will just change it and modify it by a bit so it's not exactly in its original kind of grid-like way. We'll also do that with Y. It's the random function. And this will just modify your picture so that it no longer originates from that grid-like. So let's run this. Ooh, now it looks a lot more like the final product. It's no longer in that original grid-like shape. Run it again. Ah, quite cool, quite cool. Okay, so I'm sure you guys are having quite a bit of fun with playing with this sketch, but there is one big problem. This sketch is only in black and white, and that's good. And I really do like black and white as well. But sometimes you got to add some color onto your sketch, add colors of the rainbow. So what we're going to do is we're going to modify it with this fill function. So what we're going to do is we're going to delete this since we don't need it to be white all the time. I'm going to go back into our for loop. And what we're going to do is, instead of using hex, we're going to instead use RGB as our color scale. So in order to do that, we're going to write 3 new variables, and they're just going to be called R, G, and B, setting for the RGB scale, of course. And what we're going to do is we're just going to use them to generate random color values for our sketch. So we're going to use the map function again, and we're going to take in the first one, we're going to take particles I.x. We're going to map it from 0 to width to let me just pick 40 and 200. Now, the second interval here is something that you can pick on your own free will. I chose 40 and 200, but you don't have to choose that. You could choose 60 to 100, 0 to 200, 200 to 201. It's up to you what you want to pick. This just kind of limits what kind of colors you produce on the screen. Here on the second G, we're going to use Y. We're going to map it from 0 to height, 60 to 180. And for B, we're going to do this same thing. Map it from particles I.x, 0, width, 80 to 240. Okay, so now that we have kind of generated these values of RGB, we're going to actually use it in our for fill function. So we're going to write fill, and I'm going to fill it with RGB. So these 2 variables will just replace whatever numbers you would normally place into the fill function. So let's run it again. Ooh. Yes, even though I know the results. Let's run this again. As you can tell, right now it's producing this green and purplish pinkish palette because of the way I've selected my intervals. If you want, let's try and see what happens if I were to change the values. Might not change that much, but let's see. Let's try modifying it. And ooh, kind of you can see a tinge of bluish from that area. Either ways, it's pretty fun to see the actual sketch come together with the colors. Don't forget to always play with your values while doing the code. Let's try playing with this by changing the noise detail again to see what kind of different results it might produce. Right now it's a lot more swigglier. We can also try changing the noise scale. Here's a cool thing. Let's try changing the noise scale to something a lot bigger, from 0.005 to 0.1. And you'll see that the results looks a lot more different than when you had it at just a smaller value. Pretty cool. Now let's move on to having this graph render differently. Now, if you recall from the original, you'll see that it didn't come all together. The lines kind of came in one by one. They kind of rendered slowly. And in order to have it also do that in this piece of sketch, what we're going to do is we're going to go to the draw function. We'll have a new variable called max. And this will just take the min of particles dot length and frame, sorry, 1 second. Sorry, my bad, didn't see that. Frame count. And we're also going to change the max here to also frame count. And now let's watch the magic happen. Whoa, it's now rendering from left to right. Very cool, very cool. And although it may not look like this, what this is actually doing is making it so that your picture will now render from left to right, one line at a time. It's pretty quick, so it doesn't necessarily look like it's going 1 line per second, but it's definitely rendering slowly like that. It looks pretty cool, pretty cool. You can also increase the speed by changing this frame count to a bigger value. So if I were to change it to like ×4, it will now render, may not look like it's rendering faster, but it is rendering at a faster rate, 4 lines at a time now. Okay, so, oh, wait, I mixed up. This shouldn't be frame count. This should be max, my bad. Now it should be faster. Yes, faster, faster. 4 times the speed. Okay, so now that we have it render like this, you'll probably notice a difference on, but your final product here rendered kind of randomly. It didn't, render from left to right. And you're right. It's rendering from left to right because I just declared, initialized the array from left to right, from 0 to the width, hence why it's rendering from left to right. But if you want it to render in randomly, you can go into the setup function and shuffle up your array. So that will just take the function shuffle, the array, and true. And what this will do is it'll just shuffle all the elements in your array from the original left to right, up to down, to a completely random kind of position. So let's run this again. And wow, now it's rendering in randomly. Whoa, whoa. Okay, pretty cool. Let's change the speed to 2 so we can make it slower. Pretty cool. Let's, all right, right now, I want to show you on how you can really modify the different numbers to create a certain kind of effect. Oh, one number that I do want you guys to pay attention to is this second interval here. Right now it's from 0 to 360 because there's, max 360 degrees in a circle. But I do want to kind of, right now, if I run this from 0 to 360, it has patterns like this. But if I were to instead change this to a bigger value, say 720, you can see that the lines right now have a lot more curve than before. Right before, it was a little bit kind of more smooth in its strokes and curves, but right now it looks a lot more, there's a lot more variation. And if we change it to 180, you can see that even more curves and whatnot. So yeah, that's pretty cool. There's also other value numbers here you can also play with, such as the size of your particles, the radius. You can change it to a bigger value like 4. And this will also modify your piece to look pretty different. So what I want to kind of bring through this workshop and this kind of code demo is that creative coding is really, it's really a type of code where you don't really have to care too much on like the specific rules on, oh, I have to keep this within a certain kind of range or anything like that. You should just play with it based on what you want the final project to look like. And sometimes when you play numbers, you might not even know what the final thing will look like. So like how I messed around with the noise detail and the noise scale and all these different kind of values, and see how they produce completely different results that I wouldn't have known beforehand. So pretty cool. I'm just messing around with it. And before I go, since this is basically everything I wanted to show in this code demo, I want you guys to do more of the modifications and changes on your own to really produce the kind of artwork you want. I'm going to just change this noise function here instead of from noise to random to really show you the difference that the noise function makes when creating artwork. So I've changed this to random and let's run it. As you can tell, the artwork it produces isn't the relaxing lines that we once saw before. It looks kind of fuzzy, although it does kind of produce this pretty kind of pattern, but that's probably just because the values are just too small to really see any of the random effect. So that's what this is. So hopefully with what I have, I hope you guys learned a little bit about p5.js and a little bit about creative coding to really get on your own and make your own kind of unique variation from this. In the doc link, I have the presentation, which at the very end will list a couple of changes, not changes, they're just suggestions on things that I feel like you can change in this project to really kind of change how your final art piece kind of looks like. So stop this. I hope you guys learned somewhat from this workshop, and I hope you guys have spent a good day in Dev Day. And I'd love to see some of your art pieces during the end of the day in your own project showcases. Thank you guys for coming.